Thank you. All right. So my name's Roy. Hi. I am neither a protocol guy nor a telecom guy, which means I don't know why I have my job. But it's great. I am an operations guy, and my experience is all about making things work when you can hand it a bad deal.
Bad deal.
So
Typically, when space missions get operated, decision making is done
early in the mission design phase, where it's like, oh, they'll figure it out in operations. Well, for my job to kind of figure it out in operations. So I'm happy to be here today. I'm going to talk about some challenges of implementing delay tolerant networking at Mars, and I apologize, I am out of time. Really, I don't have much time, so I'm going to go fast, and hopefully it won't be too horrible if we go fast. So let me see if I can calibrate how this thing goes. So this is what I'm going to talk about. Let me get into it. Okay, so
in preparation for this,
a lot of people that were delay tolerant network smart. And what I learned was that none of them know how to be short with their sentences. They go very, very long with their sentences. And one of the things that I was trying to understand is, what do they think DTN is and what is it good for? It should be a simple question, right? But it didn't turn out to be simple. In fact, the only thing that was a common theme that showed up when I talked about this, throwing their answers into a word cloud, was that it's all about the data and everything else is just kind of everywhere else. So that's kind of the point of my talk today, is to remind everybody that it's all about the data. And when we talk about exploration at Mars, it's all about the data we can bring back. It's not about how cool the protocols are, or wow, okay, it is cool we flew a helicopter, right? That's cool. So and that's just a thing. It's not really a data thing, but it's still a thing. All right. Anyways, so let me move on from there and just indicate that today it is all about the data. So let's move on. So but the definition wasn't satisfactory to me, so I went down some other
definitions, and with.
The first one is from his website. I don't even know who this fellow is, but at the website, and I like his wording, so I just stole it and credited him. So there he is. DTN is a network that's designed to operate effectively in extreme conditions and over large distances, such as with space communications, subject to frequent disruptions, high error rates, and latency of hours or even days. This describes Mars very, very well.
Mars is far away.
We don't have constant communications with it. We have errors in the transmission signals that happen all the time, and the latency takes time, a long time sometimes, to get the data back. So we are very worried about all of those things, and that's kind of our life. I'm not going to trouble with the lower part of this, because I hope most of you are familiar with DTN and how really at its core is the implementation of the bundle protocol. And for the deep space communications, people are leaning towards LTP as the communication thing. And then there's other things that can ride on top or beneath it, such as CFTP and BPSec, and all of those things that would be helpful. So, but when we're talking about Mars, I mentioned the long distance. Mars is a long ways away, and it gets really far away when it's on the other side of the sun, where it takes 22 minutes or sometimes a little bit more for a light signal to get from here to there, and from there to here. And so that's a long time for us. And so we have to think about what it takes to schedule communications passes when they're that far away. There is no joysticking of our spacecraft. We cannot send a signal and wait for it to come back, and what are we going to do next? I mean, it just doesn't happen. So everything that we do at Mars has to be pre-programmed so that the rovers and the spacecraft know what to do for long periods of time without human intervention. And in particular, they have to be smart about what to do if something goes wrong. So we do worry a lot about making sure that we have the right hardware on board the spacecraft, so if they're smart enough to take care of themselves. And we have to make sure that they can handle long duration sequences, which is a very different paradigm. They're pretty much everything done here and around Earth. So different way of thinking about things, and I'll get more into that point in just a minute. But the orbiters that we use, we have a bunch of them, and I'll talk about them in a minute. But we use the orbiters as our communications relay, because the orbiters can carry very large antennas, and they have typically more power than our rovers do. And so we use them as our relay. And the times that we communicate between the rovers and the orbiters is dependent upon a lot of things. I use the term lander's selectivity, and I'll talk about that in just a minute. And also an orbiter's willingness, and of course where the orbiters are. It depends on if they're in the sky or not, if you can communicate with them. And we do other things such as radiometric collections, Doppler arranging, and all that. So this is our shiny graphic that shows what the relay network really is. We've got the three Gladden assets on the left, the Curiosity and the Perseverance rover. Inside, I keep including in here, even though the mission is over, we do still listen for it in case it decides to come alive again, which we don't anticipate.
We do continue to listen.
We have the 5 orbiters down the middle, and on the upper right, we show the
three different tracking networks that we use to communicate with.
Got the Deep Space Network, which is critically important for all of the NASA activities. The Europeans use S-Track and also a couple of Russian tracking stations as well, which is part of their collaboration with the Trace Mission. All right, so if you look at from the network topology viewpoint, it's pretty busy. You know, everything talks to everything else. So every single one of these lines on here represents at least one interface that has to be developed between an organization or a piece of hardware. So it gets pretty busy pretty fast. Every connection has to be tested and verified and operated, and it takes a lot of effort to make sure that all of the connections continue to work over and over and over again. So, taking a picture there, you can see the acronyms here and figure out what that is later, right? So in any case, there's a lot of people involved, a lot of pieces involved, and a lot of computers involved in making all of this happen. So, but if we simplify it a little bit, it reduces to this. Where we've got the relay spacecraft at the top, those are the rovers from Mars. We've got the relay service provider spacecraft, those are the orbiters at Mars. We've got the deep space tracking networks, the relay service provider operators.
Those are the operators of the orbiters at Mars. We have this relay service coordination portal, which I'll talk more about in just a minute. And then the users, of course, are the operators of the rovers on Mars. So that topology is important. And as we talk a lot about interoperability, people get uptight because they want everything to use all the same protocols and network wide, you know. And so, especially in the DTN community, we all want the whole thing to work kind of with the same language, speak the same language. But I remind everybody that in operations, the only interfaces that matter to the rover operators are the ones that they see. And so there's the one at the top there with the red triangle. That's what we call the proximity link. And there's one at the bottom with the red triangle, and that's it's one of the ground system links. Those are the only ones. Everything in between is completely up to the providers to provide for them. And so they're not uptight about what's in the middle. They just want to make sure that their data gets through the system complete in a timely manner and without corruption. And that's what they're looking forward to. So when we think a lot about the implementation of the network, this was a big push-up for us to figure out. We kind of invented this thing on the fly. None of our spacecraft were designed to talk together. None of them were like the orbiters. They're all science orbiters. Their primary purpose is to do the science. And so doing relay on the side was something we had to kind of shoehorn in there and help them to do. And that was a big push-up to make that happen. One of the key things that enabled us to do that was the implementation of this Mars Relay Operations Service. It's a system that allows us to have standardized interfaces on the ground so that one rover can plug into the system and gain access to all of the relay services provided by all of the orbiters, and vice versa from the orbiter viewpoint to the landers. So it's a powerful infrastructure. So let me talk a bit about overflight selection. So I just picked, when I put the slide together, it was 27th of June. So I looked at all of the view periods of the Perseverance rover on the 27th of June, so a couple weeks back, and between the 4 orbiters that we use for primary relay purposes. And the top part is the elevation angle, the lower part is the range. And this, I was kind of surprised because typically they're not so well spaced, you know, because the orbits evolve and they overlap a lot. And so for this particular example, I was kind of surprised to see that it lined up so beautifully. And so if you look at this and you overlay on top of that how much data you think you could move through that network, it looks like that. So it looks like, based on the geometry that's available, that you could move about 4.2 gigabits of data on that day. That's a lot of data, right? And so for all of us that are in the DTM community, this is what we tend to think, oh, we can move so much data. The protocols will take care of it all and everything. But reality steps in. We've got a period of time when Maven can't support relay. We've got a period of time when the rover doesn't want to talk because it's busy talking to the Deep Space Network. We've got sunrise and sunset. We've got the workday in the middle, during which time they don't want to do relay because they're busy driving or they're taking samples or whatever they're doing. So there's lots of operational reasons why they don't want to be communicating with the orbiters. So for this particular day, that was all they chose. They chose 2 passes out of all of those passes that were there. 15 passes, they chose 2. So the operations teams had very good reasons why they only chose 2. The first of which is it was used for what they call decisional data. It's at the end of the workday, and they need to transmit the data that they think they're going to need to plan the next day's activities. So that decisional data doesn't have to be a lot. It's typically between 50 and 100 megabits. In this particular pass with MRO, if I remember correctly, with MRO, was going to exceed that. So they were happy with that. And that was good. And then they chose 1 pass later in the day to do the data dump. So one thing that's interesting about this is that if you look at the predictions too, the first one was 346, but in actuality, it came back as 225. But you have surprises a lot with how much data can actually come down. Sometimes we underperform, which was the case here in both cases, and sometimes we overperform, which is wonderful when that happens, but it doesn't happen all that often. So here, instead of getting the 4.2 gigabits, we ended up with 930 megabits. So, oh well. So there's a couple things to take from this. Some relevant operational facts. First is that the rover teams, the users of the network, scheduled their relay sessions based on a very complicated list of restrictions, including how much power was available on the rover, things that they may have been doing instead that they couldn't interrupt to do to communications. And we saw the Maven getting in the way, the Maven non-relay period. So let me go back to that real quick. So this Maven pass, it's a long pass with a relatively short range in this section that would have been good for communications. And that would have been probably the one that they would have chosen if this non-relay period wasn't in the place. But they ended up choosing the TGO one on the backside instead. All right. Anyways, and the reason they would have chosen it is because it's earlier in the night when they still have more power. So it was meaningful for them to do that. All right. So the rover teams are doing their scheduling of their relay sessions, and they are the ones that choose. So it's not the orbiters to say, oh, you're going to talk to us now. It's the rover team to say, we want to communicate during this session. And happily, the orbiters tend to be accommodating, and they're willing to work with the rover teams to make that happen. Second point that I make here is that the rover teams, they estimate how much data volume that they can return every day so that they can plan what the rover is going to do. The rover is perfectly capable of generating far more data than we could ever return through the network. So they need to know about how much data they think they can return on a day-to-day basis so that they can plan what they're going to do. There's no sense taking that data if you're never going to bring it home. So they do different kind of planning to reduce the data that they could generate to a set that they believe they can get back. And so the rover teams are responsible for doing that calculations, and that's important for them for this planning purpose. And it turns out that the proximity link, that link with the orbiters, is the throttle in the network. One would think that the throttle would be the connection between the orbiter to Earth, but it turns out that the orbiters have so much bandwidth that really is that connection with the orbiters instead. That is the throttle. Third point is that the rover teams, they actually plan to have people come in to start working on the command cycle for that day based upon when the data from the previous day is available. So they need to know precisely, or as precisely as you can, when their data, their decisional data, is going to hit the ground so they can make sure they schedule the 50 people or 100 people or however many people it is to come in to work that day. And they don't want to, so if people show up before the data shows up, they're just sitting around doing nothing, but if they show up and the data's been sitting there for hours, then that's kind of a lost opportunity for them to do more planning and to figure things out for the next day. So it's very important for us to calculate the time that it takes for us to get data back. This is what we call the return link latency. So every single relay session, it comes, we spend effort to calculate the return link latency for that relay session, and the rover teams use that actively to figure out what they're going to do. And then the last point is actually kind of a different paradigm shift. When you press send on your email, you don't care when it gets there to the recipient because you know it's going to be fast. It's going to be a few seconds, right? But you're not really worried about, well, I think I need to wait a little bit to send this email because I may want to work on it a little bit more. Typically, you don't think that way. You're right. You send it when you're ready, right? With the rover teams, though, they have to send their commands to the rover team through the network at a fixed deadline. So because they only have a certain amount of time prior to a pass before it needs to go active on the rover. So they're always on this constant march of get the data down, plan the next activities, and build the command sequence and send it up. So they need to know what is the last opportunity, the last moment in time that they can spend working on their command product before they can insert it into the network to get it on with a high assurance of getting it to the rover on time. So it's a strange paradigm because we don't really think of it that way on Earth when we're sending data to wherever. I mean, we're always like, oh, is it there yet? You know, but you're not usually thinking about how late can I wait before I send this email. Whereas with the rover teams, they're always waiting. They're wondering, how long can I wait before I have to send this command product into the network? So that requires them to do a lot of predictions in the forward link as well. Question? I don't know. I don't know. I think they're down around 250 kilobytes or something like that. So they're well compressed. We use a lot of onboard autonomy on the rovers. So with the onboard autonomy, it's mostly setting parameters and defining the time of activity starts, things like that. So it's pretty small by design, which is good. Okay. So we're not typically bandwidth constrained in the uplink direction to the rover. It's getting the data back where we're flooding the system with as much data as we can. Okay. All right. So when we talk about delay tolerant networking, our current network doesn't do any of these things particularly well. This is our kind of our wish list of how we would like to improve things going into the future. We would love addressable data transfers so that we don't have to take the data apart and know, oh, this goes to this PI and then ship it off to that PI. We want to be able to say, to have the PI, the scientists build a command product and they just get their data without anybody having to think about it. We want custody transfers where the orbiter would take ownership of the data that it has received and the rover could forget about it. But we don't operate that way right now. Right now, the rover team does a lot of work understanding what data they have received and where there's holes. And then when they think they've got it, then they will actually build a command to delete it off of the rover. So the data sits on the rover forever until somebody actually actively deletes it. So that, whereas a custody data transfer would allow them to just send it and be done with it, wash their hands and delete it right away. We don't support multiple frequency channels simultaneously. Your cell phone, way smarter than what we do at Mars. Your cell phone can communicate on a wide variety of channels, and it negotiates automatically with your cell phone tower to figure out what frequencies it's going to chatter on. For us, we actually command them actively and intentionally. So we're not good at multiple frequencies. We'd love to be better. And I mentioned this notion of the highly predictable data volumes and the highly predictable latencies. These are very important for us, but we still struggle with that. You know, you saw the predictions earlier about those two passes that they selected. We underperformed those predictions. So this is an issue for us too that we're still working through. Prioritization, we don't do so well with. We need way more capacity than we presently have. We'd like to do more with less, but we can't. We don't natively support the recovery of lost data. I mentioned the retransmission thing. We don't do encryption. We don't do demand access. We don't do always on, which means that you always have something listening, you know, when somebody may have something to say. And we don't do hands-off scheduling. It's a very manual process right now. So you could ask the question, which of these limitations might DTN help us with? And a bunch of green boxes. That makes me so happy to see. DTN could really help us with a lot of these things. You know, it would really help us to do much better in a lot of different ways. But the flip side of that, where does DTN hurt us? And that's on the predictability problem. And turns out, if we go back to the previous slide, these are the care-abouts. It hurts us in every one of our care-abouts. So strangely enough, we either have to find a way to work differently, or we need to vastly improve the amount of throughput we have, which would allow us to think differently, right? So bottom line, though, is that when you think about the one answer why DTN might be difficult to adopt at Mars, people. But no, it's actually the people. Okay, there was dots in there. Okay, so people. All right. Okay. Glad I got a chuckle. I was worried that would fall flat. Okay. Pessimism, that is actually added value. A lot of people don't think it's going to be useful. People are worried about losing control over their uplink and downlink process. They don't think it's really going to help. So there's that pessimism there. Your expectations misaligned between the DTN champions and pretty much everybody else. You know, the DTN champions are realizing this would solve so many problems, and it's true, it would solve so many problems. But most people are just like, I just need encryption, or I just need this, or I just need that. You know, see, DTN is overkill for their needs. So, or worse, it gets in the way, which is the operations paradigms and realities. You know, they don't really line up very well. Current users, we need those predictable latencies and the data volumes. The network continues to be throttled with just very few nodes, which is something we got to address. And all of our orbiters are different. So we can't really implement a single approach on all of the orbiters right now. There's the perception that it's not really ready. You know, I know there's people in this room, they'll say, yeah, it's ready. IONNet's been running for how long? I know it's okay. There's people that'll say that. But is it really? I mean, there's a lot of research going on around DTN, which implies that it's not really ready, you know? So, and this whole notion of contact graph routing, that's a work that Lee over there in the corner is working on right now. Again, it's still a work in progress. So when you say like it's ready, maybe not, I don't know. But I'm a proponent, so I'm one of the champions of DTN. I would love to see it happen. So don't listen to me. Okay. Next one, leadership. Honestly, this is probably the biggest problem right here, leadership, because we don't have managers that are operating these missions that are willing to spend money on something that they see as new or risky. So they are afraid to add this thing to their requirements for their future missions. So this is an issue that we're trying to do and trying to work through at the program level, but it is what it is. Okay, and experience, lack thereof. Most people don't have any experience with DTN. They don't know what it is. People are building new Mars missions, have no clue. And always they're like, well, I'm going to do it like I did it the last time. That's always their philosophy, because if they did it the way they did it the last time, then that's risk that they don't have to address. So people get in the way of everything all the time. Okay. All right. So closing words. At the end of the day, what we really, really need right now is to increase our throughput capacity. That is the linchpin of everything we're trying to do here. We have to have greater throughput capacity, which has nothing to do with DTN. So that's the thing that's driving it. But if we had that greater throughput capacity, I think DTN would be an easy sell, to be honest. It would simplify mission operations greatly, take people out of the planning process. It will improve I believe it would improve the return time for our data, you know, but until we have that capacity, people are not going to take their hands off the steering wheel. But even so, I think we really should be taking steps forward to implement our next generation capabilities. Things like implementing BPSec everywhere we can, doing LTP, USLP. These are features that we know we can do. And each one of these features don't necessarily make us delay tolerant networks, but it's a start to get us there. And we got to tackle this contact graph routing problem. We got to figure that out, and maybe run a parallel system for a while till we get that straightened out. And then we also have to recognize that we're not going to suddenly have a network with DTN. There's a transitional period in between. And so we got to lay the foundation for making that transition happen. And so at the end of the day, I remind everybody, it is still all about the data, you know, with a capital D. I remind you, every single pretty picture you have all seen from Mars came back through our relay network. I don't know that any of you knew that, but every single picture comes back through the relay network. So it really is all about the data. So I'm happy to be here and talk a little bit about this. And I'm done and happy to take questions, but I think I'm over time. I don't know.
I am certain that a lot of us have a lot of questions. We also have two more talks to get through. So I would propose that we stick around and address questions during the lunch hour. Try not to address too many of them right now. Maybe one or two, and then move on to the next talk.
Yes, just a question on this contact graph routing program. Why do you see that as one of the major issues? Because for me, I'm looking into the moon scenario, into the Mars scenario, there are very few nodes, and the communication topology is quite clear. You wait until you see the orbiter, you send data to the orbiter, you relay. So there is no complex routing needed in mind for these, let's say, very simple networks.
That's a great point. So right now, we don't need the contact graph routing. because everything's unidirectional. We know exactly where it's going to go. So I'm worried about the next iteration of what it's going to be. And the fact that if we want a spacecraft to not have to worry about where its data is going, we need to give it a contact graph and let it make its own decisions about who it's going to talk to first to try to get its data back. And so that requires the contact graph to be present so that the spacecraft of its own volition can try to predict the fastest path back would be to go through this orbiter at this time to get it to the DSN or maybe to S-track or whatever, and pick out the right pathing to get the data back. And that in my mind is an autonomous capability that would be very helpful, because if it isn't always the case that the first guy you can talk to is going to be the fastest route back. There are different things that get in the way of making that happen. So the contact graph, that problem of having the routing on board, that's one piece of the puzzle. But there's the operations stuff that's surrounding that. How do you build that contact graph? How do you disseminate it across the network? How do you ensure that it's updated and regularly refreshed, as the network changes and the conditions of the network change? So that's why I'm saying that that's one of the biggest problems right now is dealing with that. So,
great. Maybe one more question. Is there a quick one?
Just had a quick observation. A couple slides ago, when we talked about some of the concerns, it seemed like some of those concerns were generally networking concepts at large applied to this problem, not DTN specific.
Yeah.
So, sort of one of the thoughts was that DTN is probably the closest kind of networking concept that aligns, even though it's not perfectly aligned. And that if we tried other kind of networking concepts, it would even be farther removed. And I just wanted to understand if you felt that that was the case, or if there was something specific to DTN separate from networking concepts here that are at play.
Yeah. As I said, I'm not a protocol guy or a telecom guy. I'm an engineer, which means in my mind, there's never one best solution. There's a lot of solutions where they have good and bad things about them. So I recognize the DTN, it has a lot of green on that one slide, but that red is something I, as an operator of these spacecraft, cannot ignore. So I can either choose to live with those negatives or work around them or find other ways to deal with them, or I can find some other solution. So as of right now, I'm not a protocol guy, so I don't know all the answers about what other options are out there. But for right now, DTN looks to be like one that can help us in the future. So looking for that.
I think we should stop there. Thank you very much.
Yeah, thank you.